Okay, so here's the analytical solution. The first thing we have to do is derive the differential equation that we're trying to solve. We've made the assumption that temperature is only a function of time and not of position. So we're going to end up with an ordinary differential equation. When I draw my control volume to derive this equation, it can go around the entire object, and that's because we've decided that the entire object can be approximated as having one temperature. Right, so here's my control volume. I have in equals out plus stored. This is the first time where I've actually had to keep this stored term because it's the first time I've had a transient problem. So I don't have anything going in. I have convection leaving, at least that's the way I've chosen to draw the arrow, and then I have stored, which is du dt. So this is my ODE written in terms of energy. It makes perfect sense. Again, I have a change in energy storage related to how much energy is being pumped in or lost due to convection. If I want to get a equation, an ODE written in terms of temperature, I need some rate equations. So for convection, I have Newton's law of cooling, right? So h bar times a sub s times, I've drawn this arrow as leaving, so it would be T minus T infinity, right? The surface temperature and the temperature everywhere is the same, so this is T minus T infinity. And then du dt takes a little bit of thinking about. The total energy inside of this object is the mass times the specific internal energy. So I need to take the derivative of that, right? The mass is not changing for this control volume, so I can pull that out. So this is m times du dt. And we're going to make the approximation that this is an incompressible substance, which means that I can write that U is equal to, du is equal to C dt, right? So du d time is equal to du d temperature times d temperature d time, right? And du d temperature, that is the definition of the specific heat capacity for an incompressible object. So du dt, where U is big U, is mass times the specific heat capacity times d temperature d time. This mass times specific heat capacity is the total capacitance of the object. All right, so we make this substitution, we make that substitution, we get this equation here. We'll do the usual thing, which is take the highest order derivative and divide through by everything that's constant. So we're dividing through by m times c, and put all the temperature stuff on one side, and you get this equation here, right? We have h bar times a sub s divided by m times c times temperature, and then on the other side we have h bar times a sub s over m times c times T infinity. And this quantity right here is just the inverse of that lumped capacitance time constant, right? We have R convection times big C, which is mc divided by h bar times a sub s. So this is 1 over tau. So here's our differential equation. If I take this particular T infinity function and plug it into here, I get this differential equation here that we have to solve. Okay, so that's the process of deriving the differential equation. You have to do that yourself, right? Every problem will be a little different. Solving this can be made really easy using Maple, but I think it's something you ought to know how to do, so we will talk about that. Hopefully this is a review. Certainly we've seen equations like this when we were doing extended surface problems. This is not a separable equation, right? So we're going to break it up into a homogeneous and a particular solution. That's exactly what we did when we were doing extended surface problems. So I make this substitution here. I get this equation here. I'm going to break it into the homogeneous part and the particular part. So the homogeneous part has to be a homogeneous differential equation, so I have to take this part of it and set it equal to 0. That's a homogeneous differential equation. And whatever is left over is a particular differential equation. So these are the two differential equations that I have to solve, right? This one you could look up. It's exponentials. This is actually separable, so you could go through the steps of separating it, right? You bring all the temperature stuff to one side, all the time stuff to the other side, integrate both sides. This is the log, and then this is minus t over tau plus c. If I want to solve for th, I take the exponential of both sides. So here I have the exponential of this stuff. This is the exponential of minus t over tau times the exponential of c, which is my undetermined constant. So here's my homogeneous solution. hopefully this is something you've seen several years ago many times, but this is the solution to the homogeneous differential equation. Now I have to solve the particular solution. So we talked a little bit about this also when we were dealing with extended surface problems. And the way to deal with this is use the method of undetermined coefficients, right? So the method of undetermined coefficients looks at the right side, right? It looks at the non-homogeneous terms in this equation, and it says I'm going to assume that my particular solution has all of those functions in it as well as their derivatives. So but all of them multiplied by some undetermined coefficients that I can adjust. So if I look over here, I see a constant, so C2, I see a linear term, so C3 times t, I see a squared term, and then I see a cubed term, right? And then I have to have all of their derivatives. Well, the derivative of a constant is 0, so I don't need that. The derivative of a linear term is a constant. Well, I already have a constant, so that's fine. The derivative of the squared term is a linear term. I already have that. The derivative of a cubed term is a squared term, and I already have that. So this actually is all of the terms over here as well as all of their derivatives, right? So I take this idea, and honestly, in this process, coming up with this functional form with these undetermined coefficients is the only hard part, right? Because once you get to this point, you just plug this into here and you adjust these constants so that you solve the problem, right? So here, I'm going to take this particular solution and I'll plug it in here, and then I'll take the derivative of this thing and I'll plug it in here, right? So I take this and I plug it in here, and I take the derivative and I plug it in here, right? So here's my particular differential equation with this substituted into it, right? So now we have to just adjust these constants so that I have a solution to this differential equation for any value of time, right? So what that really means is that all of the constant terms here, so this guy and this guy and this guy, they have to take care of themselves. They have to balance themselves out, because I can't rely on any of these other terms to do it because time is changing, so they'll all be changing, right? So I'm going to get an equation here for all of the constant terms. It'll be C3 plus C2 over tau plus A0 over tau. And then all of these linear terms, so this guy, and this guy, they all have to take care of themselves, and they give me this equation here. All of the squared terms, they have to take care of themselves. So that's what gives me that equation. And finally, the cubed terms, which is this guy and this guy, they give me that equation. So what you should end up with, if you've done it right, is, in this case, 4 equations in my 4 undetermined coefficients, right? So I can solve these. They're actually not that hard to solve. You start down here and solve for C5, and then C4, and then C3, and then C2. Or I'm just going to throw these into ease. So somewhere is my ease model. These are the same equations, and ease will happily tell me what is C2, C3, C4, and C5, right? So that's my undetermined method of undetermined coefficients. So I have my homogeneous differential equation. I have my particular solution. I add them together, and I get my general solution, right? So I know what these guys are. These constants are no longer undetermined. I have them. This guy here, though, is still undetermined, C1, right? This constant here. So this solution will solve this differential equation no matter what value of C1 I choose, right? So I have to choose C1 to satisfy the boundary conditions, which is exactly what we did when we were doing this kind of problem before. My boundary condition is at time equals 0, right? At time equals 0, I have to make sure that I get the initial temperature. So that's what this is. So I plug in time equals 0 here. So here's everywhere there's a time, I plug in a 0, and I get C1 plus C2 is equal to T initial. So that's how I solve for C1. And that gives me the solution, right? I come over here and I make that substitution here, and I get exactly the solutions that we talked about. In fact, that's where I made these plots, right? So it obeys my intuition according to the time constants. This is the one I get. If I reduce the time constant by a factor of 100, it does this, right? If I increase it by a factor of 100, it does this. Before we move on, the other situation you often run into is a situation where you have some kind of a repeated forcing function. So what that would be in a case like this is you would have this pulse of temperature, but it repeats itself over and over and over again, right? And if you think about what the object's going to do, well, the object initially starts at 0, and during the first pulse it warms up more than it cools off, right? And then during the second pulse it warms up a little more, and eventually what happens is it comes to this situation where it undergoes a cycle that begins and ends at the same spot. So you might call that cyclic steady state, right? So at some point you're going to get the object doing exactly the same thing for every single pulse, right? Initially you have a little bit of a warm-up period, but eventually every single pulse the object does the same thing. And it's often the case that you really only care about what happens after this initial unsteadiness has died out, right? So you really only care about the case where you get this cyclic steady state process. So how would we get that using the situation, using the solution that we have here? How would we adjust our boundary condition such that we get the cyclic steady state rather than this first pulse response, right? Right now what we have is the response during this first pulse. What I really want is this cyclic steady state. And it's really just a matter of realizing that rather than enforcing the temperature at time equals 0 is equal to T initial, here I want to enforce the fact that the temperature at time equal to 0 has to be equal to the temperature at time equals T cycle, right, 0.4 seconds. So that's what I would use to get C1, right? So if I plug in on the left side this equation with time equals 0, I get that. If I plug in on the right side this equation but with time equals T cycle, I get that, right? And that's a perfectly legitimate boundary condition. I can go here and I guess I would get rid of this, and let's do this, and then I do this to do that last boundary condition. And now I'll hit solve, and with any luck, if I come up here and overlay on this plot the solution that I just got, yeah, this is my cyclic steady state, right? You'll notice that there's an attenuation and a phase shift. That's always what you're going to get when you have an object that's basically a first order object responding to some kind of repeated impulse, right? This ambient temperature peaks here. My object peaks over here, right? This ambient temperature changes by what, 470 degrees? My object only changes by, I don't know, 30 degrees, right? So there's an attenuation of the response and there's a phase shift, right? The bigger I make my time constant, so let's make my time constant bigger. I'll just multiply the density by 100 and we'll solve again. And we'll come in here and update. You'll see that now my object really doesn't do anything because its time constant is now 29 seconds and it doesn't really have time to respond during this 0.4 seconds, right? So it's taken it a long time to get to this steady state, but when it finally gets to this steady state, it basically sits here at some temperature such that the amount of energy it gets when the ambient temperature is above its temperature is exactly balanced by the amount of energy it loses when the ambient temperature is below its temperature, right? If I make the time constant really small, so now instead of multiplying by 100, let's divide by 100 and solve. What I should see is, yeah, now my object sort of follows right along with the ambient temperature, right? So not much attenuation or phase shift anymore. Now the time constant is really small relative to the period of the forcing function. Okay, so that is the analytical solution. And what we should do next is at least start talking about numerical solutions, and we'll finish that up in the next lecture. But let's at least start talking about how we would get a numerical solution to this kind of a problem.